Hey y'all, welcome back to Coding with Minmer. On today's agenda, we're going to tackle LeetCode problem 34, find first and last position of element in sorted array. After that, we'll go over two actual variants of the original question that Meta asks, one of which will really make you reflect on your life and whether you truly understand binary search or not. Okay, no more dark thoughts, let's get into the problem description. We're given an array of integers called nums sorted in non-decreasing order. In our example, here's our nums in which all the numbers are in non-decreasing order. What's that mean? It just means the following number is either the same value, like it is here, 3 to 3, 9 to 9, 12 to 12, or it's increasing. For instance, from 3 to 9, 9 to 10, 10 to 12, you get the idea. In my opinion, non-decreasing order is kind of a confusing term, but we just have to understand that if a vector is non-decreasing, it means there could be duplicates. Anyway, our task is to find the starting and ending indices of a given target value. If the target is not found in the vector, we're instructed to return the indices -1, -1. In our example, we have a target of 9, and therefore we'd like to find the leftmost 9, take note of its starting index, and then find the rightmost 9 and take note of its ending index. It's implied, so the problem description doesn't really mention it, but the starting index must be the first element in our result, and the ending index the second element. Ultimately, this is our result, and that's what we'll return in our function. And you'll see in the code later, we name this vector result. Alright, the requirements now make sense. We roll our eyes and scoff in pure arrogance because we already have a solution in our minds. We can intuitively loop left to right. In the moment we encounter our target value, we already have 1/2 of our answer. Now here's the key piece of logic. We'll keep looping until we either hit the end of the vector, or more likely, when we encounter a 9 whose following element is different. Here, indeed, 9 is not equal to 10. So we know for a fact that we just found the ending index of our target. I'll emphasize it real quick. This if statement check is very important for the variant. Okay, so we swiftly solved the problem, only to realize we missed a very important requirement of the problem. We're supposed to come up with a log n solution. Our eyes start bleeding at the thought of it because what is the only search algorithms that have a log n time complexity performance? You guessed it, it's indeed binary search. But how? We're skeptical, but a binary search does sound possible. We do have a lower bound value, an upper bound value, and everything in between is sorted. The only confusing thing is that there are duplicates. Let's just YOLO and try a binary search and see what logical decisions we can make on any given iteration. Of course, we have our classical left and right pointers. On the first iteration, what's the middle index? Well, the left plus right divided by 2 is 6, so that's where the middle index will be at. Well, we immediately found a 9. Are we done? No, we wanted to find either the leftmost 9 or the rightmost 9, either of which will be part of our answer. Let's do things one at a time though, and sure, try to find the leftmost 9 in this binary search. Therefore, I guess we have to traverse to the left, even if we found our target, in hopes of getting ever so closer to the leftmost 1. We revise our pointers. The left pointer remains where it is, the right pointer is m-1, and we recalculate the middle index to now be at index 2. We have a value of 3. Since it's lower than our target of 9, it's quite obvious we should traverse to the right. That much is ordinary for a classic binary search. We readjust our pointers, this time shifting L to m+1. The right pointer remains where it is, and now the middle index is at index 4, where we have yet another 3. We know what to do. Our answer must lie to the right, so let's go in that direction. On the next iteration, we find that all the pointers L, R, and M land on the same index, index 5. We have a 9, which happens to be the leftmost 1. Do we stop here? According to our algorithm, no. We traverse left even if we find our target of 9. Or a bigger number than 9 for that matter. Like if the middle index was at this 10 or either of these 12s, we'd surely go to the left to get closer to our target of 9. Anyway, we go to the left by reassigning the right pointer to m-1, But hold up, the 2 pointers left and right have crossed each other. That's where we stop. A simple observation leads us to believe that where the left pointer ends up does point to the leftmost 9 with a starting index of 5. Little did we know, we actually just deduced lower bound binary search. It's typically used to find the leftmost occurrence of a target number. And if it's not found, the first greater element would be returned. That's literally the definition. And to formalize this logic, if we encounter a number that's equal or greater than our target, we will go left. Otherwise, go right. With that said, let's note down that starting index of the 5 in our result vector. Now, this immediately makes us think, if we can use lower bound binary search to find the leftmost 9, is there such a thing as upper bound binary search to find the rightmost 9? Yes, there is. It's just the inverse of the lower bound binary search. That if we encounter a number that's equal or lower than our target value, we go right. Otherwise, if it's greater, like this 10 or 12s, then we go left. Okay, let's give this idea a try and speedrun it. On the first iteration, the middle index is again at index 6 with a value of 9. We've found our target of 9. This time we'll oppositely go to the right. Therefore, we adjust the left pointer to m plus 1. The right pointer remains where it is. What's the middle index now? It'd be at the 9. Whose value is also 9, what do? We go to the right in hopes of finding the rightmost 9. Readjust the pointers as such. The middle index will be at index 11. We have a 12. That's way too big, greater than our target of 9. Let's go left. The right pointer will now be m minus 1. Left remains where it is, and the m will also be at index 10. A value of 10 is still too big. Let's go to the left to be closer to a 9. The right pointer then will be at index 9, left at 10, and we stop our binary search because the 2 pointers have crossed. Making a simple observation, the right pointer ends up where the rightmost 9 lives, with an index of also 9. It just happened to work out that way. This is great though, we found the ending index. Our binary search was a success. We put the 2 indices we found together, 5 and the 9, and that's our answer. Amazing, it turned out we needed 2 types of binary search to conquer this problem. But wait, there is more. As if this problem wasn't difficult enough, there's an influx of edge cases. No thanks to these constraints. But it's okay, we'll go over each one with their own example. Okay, first off, what if we're given an empty vector? Well, in this case, it doesn't matter what our target is, it won't be found. Therefore, we'll listen to the problem description and return indices -1, -1. Next up, let's take a look at the second example. What if our target is over 9,000 and happens to be larger than all the elements in our vector? We know this to be true because our vector is sorted. Therefore, we can have an easy if statement to check if the target is larger than the last element. If it is, we'll also return -1, -1. 9001 doesn't exist in the vector. Now let's change this up. What if we had a target of, say, 1? Well, we can make the inverse if statement that if the target is less than the first element in the vector, we know that it also cannot be found. We'd return -1, -1. And yes, if you're a binary search master, you'll note that this if statement isn't necessary for the code to work. I won't go into it, but at the very least, this if statement would be a micro optimization and make the code a bit more readable. Alright, lastly, what if the target is not found within the array? In other words, it's not lower than the first element and not greater than the last element. It's somewhere in between, but it's just not found. Well, we can dispatch a binary search to find the leftmost 4, but if you try it out, you'll find this 6. Therefore, we'll sneak in another if statement to see if the leftmost number that we found is indeed our target. Here, it's obviously not, so we return -1, -1 as the indices. Okay, that wraps up all the other logic. The time complexity is the accomplished log n, and the space complexity is big O1. We only really use pointers like the left and right pointers. Okay, let's write this up. Okay, first things first, let's tackle the edge cases. What happens in the case that our given vector is empty? Well, we can return the 2 indices, -1, -1. That's what the problem told us to do. If we got past that, there's still two more edge cases. What if the given target is less than the first element? Or if the given target is greater than the very last element? Well, in these cases, we'd also return -1, -1 as well. If we made it to line 8, let's initialize our vector called result. It'll hold the two elements, the starting index and the ending index. Let's make sure we return that before I forget. Now here comes the bulk of the logic. Let's initialize our left pointer as well as our right pointer to ready ourselves for the binary search. Now the very first one will be to find the leftmost value that equals our target. As per usual, we'll keep going in our binary search as long as the two pointers don't cross. We'll compute the middle index. Now, if the value that we found at this middle index is equal or greater than our target, then we want to go to the left. Otherwise, if the value found at middle is lower than our target, we obviously want to go to the right. We adjust the left pointer to be middle plus 1. Once we've exited our binary search, wherever the left pointer is will be the starting index of our answer. But wait 1 second, there's one last edge case. That if the leftmost number that we found, nums at left, is not equal to our target, we also want to return -1, -1. Okay, but if we secured the starting index, we need to do one more binary search. Let's reset our pointers left to 0 and right to the very last index. I'm going to do a very terrible thing and copy and paste. Don't be like me, but I just want to speed this up a bit. The only changes we have to make is reverse the logic. If the number we found is equal or lower than our target, then we're actually going to go to the right. Otherwise, we're going to go to the left. Okay, when that's said and done, wherever the right pointer ends up will be the ending index, or in other words, the rightmost element that equals our target. The second element in our result then will equal this right pointer. Okay, that was a lot of code, but good job, we made it. Let's get into the first variant. Meta may ask you a slight variant of the original LeetCode problem, where the only thing that's different is that we're now supposed to find the count of a given target value. For some context to build off of, let's look at our example from the previous problem and reinspect what we did for the OG problem. We had dispatched two binary searches. We ran a lower bound binary search to find the leftmost 9 here with an index of 5. We put this as the starting index in our resulting vector. Remember, we called it result. Then we ran an upper bound binary search to find the rightmost 9 with an index of also 9. We include that as the ending index in our result. That's what we did, and that's what we returned. Fast forward to this variant, if we're now being asked to find the count of our target of 9, and if we already found the starting and ending indices of the target, can't we just minus the 2 to get the number of times the 9 has occurred? Here, that would be 4. Let's verify that real quick. 1, 2, 3, 4, 5. Whoops, there's an off by 1, and that's because we're working with indices. Let's compensate by adding 1 to get 5, and that is indeed the answer. The count is 5. That's pretty much it. The edge cases from the previous problem still exist, but they're still handled from the existing code. The only difference is, if the target is not found in the array, we return 0, not the -1, -1 indices. That makes sense to me. The time complexity is the same. It's log n, and the space complexity is big O1. Alright, there's not much to change. Let's get into the implementation. Let's take a look at our method signature here. It now returns an int for the count, no longer the indices. The first two if statements of our code are to capture the edge cases. And if either one is executed, we're going to return 0 instead of the two negative indices. If we never found our target to begin with, then it's occurred 0 times. There's one more invalid state we can enter. It's on line 20. Let's also return 0 there. The last thing we do is some quick maths. Let's find the count by minusing the ending index with the starting index. Remember to plus 1 because we're working with indices here, and that's it. This modification wasn't too bad, but the next variant is significantly different than the OG problem. Let's get started. To me, this variant does a great job building off the original LeetCode problem and really challenges you to cleverly use binary search. It's a good twist that'll help you in future LeetCode problems. Okay, let's read the problem description. We're still given an array of integers called nums sorted in non-decreasing order, but now we want to find the count of unique elements. That's the key word there, unique. Let's take a look at our example. Here's our vector of numbers. It doesn't take a genius to know that there are 3 unique elements, 5, 8, and the group of 9s. As the how to solve this, we can intuitively loop left to right, and when we encounter the rightmost 5, then we can safely increment a count variable to 1 to say, hey, we found a unique element, and we know this because the following element is different from it. 5 is indeed not equal to 8. Furthermore, we're confident to not double count any 5s because we had passed all the previous 5s already. If you remember, I hinted earlier in the OG problem that this piece of logic is very important for the variant. We continue our loop to find the rightmost 8, where its following element is 9. We'll increment our count to 2 to capture the unique 8. And then we continue our loop until we hit the last 9, where there is no following element to it. This is an edge case, but whatever, we handle it, and we increase our count to 3. And we're done. The result is 3, and that's what we return. This is a big O and time complexity because we had to process every single element. As always, there's a big gotcha. Look at what time complexity we have to come up with. It's k times log n, where k is the number of unique elements. Therefore, if the log n part is the binary search, then the problem is essentially telling us to run binary search for each unique elements, for k elements. In regards to our example here, we'd have to run binary search 3 times, once for each unique element, 1 for the 5s, and then 1 for the 8s, and lastly, 1 for the 9s. But how do we do this programmatically? Well, thanks to the binary search skills we picked up from the OG problem, we know there are 2 types of binary searches. There's a lower bound one, as well as an upper bound one. My question is, can we reuse either one? If so, which one? Well, here's the intuition. In the naive solution of big O(n), we concerned ourselves with finding the rightmost element of every single element. Can't we use the upper bound binary search for exactly this to find these elements? Well, yes, we can. We can enter a while loop with a pointer, say I, because it's traditional, and dispatch the first binary search to find the rightmost element of the 5s. And recall from the original LeetCode problem, we had established that with an upper bound binary search, the right pointer will always end up at the rightmost element of the target. We can double check visually that this is the rightmost 5. The following element is different. It's an 8. Therefore, we're safe to increment our count. So far, we have 1 unique element. It's the 5s. Great. Now, how do we progress our while loop? Well, we can reassign the pointer I to the right pointer plus 1 to be at index 4. Thereby, skipping all of these 5s, that's exactly what we want to do. Just like that, we're very ready for the next iteration to run our second binary search. Okay, so into the new iteration, where do we put our pointers? Well, again, we don't want to double count any of the 5s. We already captured that. So we'll initialize the left pointer to exactly where I is as the new lower bound. And the right pointer will be at the last element to include the rest of the numbers. Sure, let's go through the binary search workflow. Even though I've done it a dozen times already, why not? Where's the middle index? It's computed to be at index 8. We have a 9 that's greater than our target of 8. And by the way, we know the target to be 8 because that's where our I pointer points to. That this is the value we want to find the rightmost element of. Okay, yeah, so 9 is greater than 8. We're going to go to the left to get closer to the rightmost 8. We readjust the pointers like so. The right pointer is at m-1 at index 7. We continue on. Where's the middle index now? It'll be at index 5. Here, we found exactly the target. But remember, we want the rightmost one. And according to an upper bound binary search, we want to go to the right. Therefore, the left pointer will be at m+1. The right pointer remains where it is. And the middle index is now at index 6. Same deal, you have an 8, let's go to the right. We readjust the pointers, they're all going to end up at index 7. Where we have a 9, it's too big, let's go to the left. The right pointer will be at index 6, crossing the left pointer, and there you have it. The right pointer indeed points to the rightmost 8 with an index of 6. Therefore, we'll do two things. We'll increment our count to 2 to capture the 8s, and then repoint the I pointer to right plus 1 at index 7. We're getting the hang of it. We move on to the next iteration and initialize our 2 pointers for a binary search. We run the upper bound binary search, and I'll just tell you right now, the right pointer will end up on index 12. Fantastic. The value it points to is indeed the rightmost 9. Therefore, we're going to do two things, increment our count to now 3, and reassign the I pointer as appropriate. On the next iteration, however, I has exhausted every single element. We're done. We not only have our answer of the 3 unique elements, but we also ran our binary search of log n 3 times, or in other words, k times. We achieved the time complexity that we set out to accomplish. The space complexity is still big O1 since we only used fixed variables. Now, if you're a smarty pants, you may be questioning this time complexity. And sure enough, so will your meta interviewers. Let's take a look at some examples. What if we're given a vector of all duplicates of all 1s? Well, we need one binary search, and of course, binary search is log n. What's the time complexity then? It's simply log n. This is considered the best case. Okay, but how about this? What if we're given all unique elements? Well, we'd run a binary search by the number of unique elements, which in this case there are n unique elements, 1, 2, 3, 4, the length of our vector. Therefore, we have n times the binary search, which is log n. This is considered the worst case. We'd rather go with the big O(n) approach that I previously described. Okay, with my bases covered, let's go through the code. Before we code this up, take a look at our method signature. We're returning an int to return the count of unique elements, but you'll also notice we're no longer given a target. Implementing this, what are the 2 variables we need? We need one, the count, which will ultimately return, let's do that before I forget, and then secondly, a pointer I that we'll use as a left pointer in our binary searches. Let's enter a while loop that as long as there are elements to process, we'll keep running binary search. Okay, so for each binary search, we know the target will be the value at the current I pointer. That's the element we'll want to find the rightmost element of. What's the left pointer? It will be anchored at I to potentially exclude all the numbers we already processed. And the right pointer, as always, will be at the very last element, at the last index. We'll enter our upper bound binary search, where we'll keep going as long as the 2 pointers don't cross. We then compute the middle index, which remember is simple maths. We add the 2 pointers and then divide by 2. Then we'll compare our value at this middle index with our target. If it's lower or equal to the target, we want to go to the right. We'll adjust the left pointer like so to get ever closer to the rightmost element. Otherwise, we're going to go to the left, adjusting our right pointer like so. Now, once the binary search is done, we can safely increment our count variable to count the unique element, and then to set ourselves up for a successful binary search on the next iteration, we'll reassign I to right plus 1, just like we saw in the diagram before. Okay, that is it. This was great usage of the upper bound binary search. I hope it made sense. Good luck on your interviews. And if you learned something today, please make sure you like, comment, and subscribe. Thanks for watching.